Hello everyone. We have seen that when a current carrying loop is taken, then it behaves as a magnet and it has a dipole moment, and that dipole moment, the value is given by I, the current, into A, the area. So the magnetic dipole moment due to a current carrying loop is given by I into A. Now we are going to discuss the same thing but in a bit different manner. Actually, what we are going to do is we will take a current carrying loop, but not exactly a current carrying loop. It is in the form of an atom where an electron is revolving around the nucleus in a circular orbit. So when the electron revolves around the nucleus in a circular orbit, this also behaves as a current carrying loop. Obviously, the direction of current is opposite to direction in which the electron is revolving. So we have a current carrying loop, and for that current carrying loop, which is because of the revolving electron, there is a magnetic dipole moment of that particular atom. And we are going to calculate that magnetic dipole moment of the atom due to the revolving electron. So let us see how it is done. Here you can see we have a revolving electron. The direction in which we can see that the electron revolves, if we take the top view, then it is in the anti-clockwise direction. So obviously the direction will be of the current will be opposite to it, that is in the clockwise direction. So this will be the direction of current as I am showing you here, and let it be given by I, which is opposite to that of the direction in which the electron moves. Now the velocity by which the electron moves, it is v, and it is shown by the tangential direction to the circular path. Me represents the mass of the electron and r is the radius of the atom. You can say it is the distance of the electron from the center of the nucleus. Now the angular momentum, if we want to find the value of angular momentum, you must be knowing that angular momentum in terms of vector notation, L is equal to R cross P, where P is a momentum, the linear momentum. The direction of P is along the direction of V, so momentum P will be given by mv, right? So here you see, if we want to find the value of L, the magnitude, it can be calculated very easily. See here, I am writing it down here. Say L is equal to R cross P. So the magnitude will be given by R P sine of the angle between them. Okay. Now sine of the angle, to see the angle here, the direction of R, the radius vector is in this direction, and P is in the direction of V. Velocity and momentum are in the same direction. So this angle, you can see here, the tangential direction and the radial direction, this will make an angle of 90 degree here. So we will put 90 here, and sine 90 is 0. Sine 90 is 1. So we have RP, where R is the radius, and so the value of P is written as mv, mass. Here the mass of electron is me, into the velocity of electron is v, and r is also there. So we can write mvr. This is the value of the angular momentum of the electron which is revolving around the nucleus. We will need this value in the later stage of this derivation, where we are going to calculate the value of magnetic dipole moment. So I hope this is clear. Now what we are going to do is to find the value of the magnetic dipole moment. We know that the value of current is I, which is in the clockwise direction here. Now we know that the formula for vector L is given by R cross P, and if we use our right hand thumb rule, that is the curve fingers from R to P. The direction of L will be in the upward direction as shown here. So if this is clear, now we are going to find the exact value which represents the topic, that is the magnetic dipole moment we are going to calculate now. So let us see how it is done. This is a diagram which we have taken. We have already considered the same thing. Now see here. We know that value of M, the dipole moment, is given by I into A. That is, we need the value of current and we need the value of area. The value of current is Q by T. So here it is charge E. E is the charge on an electron, which is the charge which we generally represent as Q, divided by the time period. The time taken to complete one revolution around the nucleus is capital T. So if we study a particular point, so from that point E charge will pass in T time. T is the time period. So we write E by T as the current. Okay, where the value of T, the time period, will be given by distance, which is 2 pi r, which is the circumference, divided by the velocity. So T will be given by 2 pi r upon V. So now let us put the values and to find the value of I here, which is E by 1 by T. So 2 pi r upon V comes to the denominator. So we have the value of I, current, as EV upon 2 pi r. The value of area we know, it is pi r square. So finally the value of M we need to calculate. M is the dipole moment, and the value of the dipole moment, as you can see here, we have calculated it. The value of I is here, so we put the value of I here, and the value of A, because dipole moment is given by I into A, so we put the value of A here. So you can see the terms which cancel out, this R and the squared term will cancel out, and we will be left out with EVR upon 2. The pi term will also cancel out here. So we are left out with EVR upon 2. So I hope this is clear to you. Now, if this is clear, then we can represent this magnetic dipole moment in terms of vector also. And firstly, in terms of L, we will represent. We have already calculated the value of magnetic dipole moment as EVR upon 2. And we have also shown that the value of L, that is angular momentum, is ME into V into R. Now VR can be written as L by ME. So if we replace VR here, so what will be the value of M that we will be getting here? Here we are writing VR as L by ME, and we are putting this value of VR here. So the value of M will be E by 2 into L by M. So we put this value and we get the value of M here as shown. I hope this is very clear to you. So here the value of M in vector notation. To understand the direction of L, we have already mentioned that L is in the upward direction. The direction of M can be concluded, but you see here the value of M, the magnitude we are getting as E by 2M into L. Now when we want to find the direction of M, that is the dipole moment, you see here the direction of current, as I have mentioned earlier, it is just opposite to the direction in which the electron flows. So the current is in this direction. So if the current is in this direction, clockwise direction, so this pole, as we see it from the top, the direction of current is clockwise, so this behaves as the south pole, and north pole is below it. So naturally the direction of dipole moment is always from the south to the north, that is in the downward direction. This will be the direction of dipole moment, which is given by capital M. So therefore we can conclude that M, that is the dipole moment, and the direction of the angular momentum L. They are opposite to each other, so they will cancel. They are opposite to each other, so if we write the vector sign there, so one will be represented by the negative sign here. So I hope this is very clear to you. So now M can be represented, vector M can be represented as minus E by twice ME into vector L. Vector L and vector M, they are in the opposite direction, so that's why the negative sign is here. Now, according to Bohr's atomic theory, and the postulates are there, that whenever an electron revolves around a nucleus, its angular momentum is an integral multiple of, if you remember it, it is an integral multiple of h by 2 pi, which we can see here, where n generally represents the orbit number, or it is the principal quantum number. Suppose the electron is in the first orbit, so the value of n will be 1. In the second orbit, the value of n will be 2. Second orbit is also considered as first excited state. So in the first excited state, the value of n will be 2. In the second excited state, the value of n will be 3. And accordingly, we can consider. So the magnitude of M, the value of L can be replaced by NH by 2 pi. And so we are having a value here where N is the value which can change if the electron moves from the first orbit to the second to the third. So the value of N will change. Otherwise, all the terms, E charge on an electron, H Planck's constant, 4 pi, and M mass of the electron remains constant. So this is constant quantity and we call it Bohr's magneton. Okay. So this is Bohr's magneton which we consider here. So the magnetic dipole moment of an electron revolving around the nucleus, or we can say the magnetic dipole moment of the atom, will be given by N into EH by 4 pi ME, where EH by 4 pi ME is the Bohr magneton. Okay. Now see here, this Bohr magneton can be defined as the magnetic dipole moment associated with an atom due to the orbital motion of an electron in the first orbit, that is n is equal to 1, of hydrogen atom. That means if we put here n is equal to 1, then the magnetic dipole moment is EH by 4 pi m, and this represents Bohr magneton. What we can simply say in one line is that the magnetic dipole moment of an hydrogen atom in its ground state, where the value of n is 1, that magnetic dipole moment is known as Bohr magneton. And if we put the values of these constant quantities, like the value of E we know as 1.6 into 10 raised to the power minus 19 coulomb, the value of H, Planck's constant, is 6.62 into 10 raised to the power minus 34 joule second, 4 pi, you know the value, and ME, the mass of the electron, is 9.1 into 10 raised to the power minus 31 kg. So if we put all the values and if we solve it, then it comes to be 9.27 into 10 raised to the power minus 24 ampere meter square. You remember this unit, ampere meter square. It is the unit of dipole moment, because this is also, Bohr magneton is also a dipole moment of an hydrogen atom in its ground state. So it is ampere meter square. So I hope this is very clear to you. This is a very important topic in which we have discussed that when an electron revolves around the nucleus, it behaves as a current carrying conductor where the current direction is opposite to that of the direction in which the electron moves. And accordingly, it gives rise to the magnetic dipole moment of an atom. And that magnetic dipole moment of an atom we have calculated here. Okay. So I hope this is very clear to you. Any doubt, you can post me the doubt. Thank you.